Can you hear me well? Okay. I'd like to first of all thank Sanjib for inviting me here. I'm Yongjoo back from SNU at KAIST. It's actually my third time here. My last visit was like almost 10 years ago, I think. And at that time, I was just beginning my postdoc studies. Now I'm a professor, and it's really good to be back here. And I can really see that the city has grown a lot. Considering the level of traffic that we have seen in the morning. Today I want to talk about some recent project that we are trying to now write up and maybe get some feedback from the audience, which is about quantifying the information flow in stochastic trajectories. I actually guess that Sanjib expects me to talk about active matter probably, because I was also doing some work on the phase separation in active matter. But actually I thought that since I gave that talk many times before, I would switch to a new topic and maybe talk about some interesting result we found out in this discipline. So, well, this work was done with the help of Maxwell demon hunters in my group. So maybe the name would remind you of these beautiful ladies. But actually, they are these wonderful gentlemen, Yongjoo and Kwon. They are my students. So, as you could have guessed from this Maxwell's demon included in the previous slide, this study is basically about Maxwell's demon. So, it was almost 20 years ago, there was some very influential studies by Takaru Sagawa and Ueda in Japan, who really clarified how Maxwell's demon should be interpreted in the thermodynamic sense. So, so basically what we have to bear in mind is that when the system, all systems can be divided into some subsystems which are exchanging energy as well as information. And this information flow is constraining the direction of the energy flow. So when you want to interpret this Maxwell's demon somehow appearing to make the system violate the second law of thermodynamics, you should actually consider that the kind of inequality satisfied by the system is not actually about the entire universe. The entire universe consists of the system and the Maxwell's demon. And when you want to think about the kind of second law-like relation for the system, then you have to bear in mind that it's not the entire universe, but there is some kind of extra thing going on between the daemon and the system. The daemon can measure the system, the state of the system, and then do some kind of feedback protocol on the system. And the amount of information which is built up between the daemon and the system determines how much you can appear to violate the second law of thermodynamics. So this should have been zero, but when there is some kind of non-zero mutual information, and then the bound can be actually less than zero.
So question,
yeah.
Information flow is the same as the entropy flow?
Sorry?
Information flow, that's the same as the entropy flow?
It's not really the same, but it's part of the entropy production. So when you consider entropy production, you have to always think about some information contribution to that, as well as the energetic contribution to that. Well, but okay. Let me move on to some further updates which has been occurred in this discipline. So, that was 20 years ago, so now we have a more detailed picture of what is happening here. So mutual information, which was used in the previous inequality, is actually a symmetric quantity. So even if you exchange x and y, still the mutual information will remain the same. The value will remain the same. So it is not really showing you how the information flows between two subsystems. But then you can now also define information flow, which you can motivate by actually taking the time derivative of this mutual information. So when you take time derivative of mutual information, you actually get two quantities. The first one comes from the change of mutual information due to how the future state of the x part has some kind of information about the current state of the other part of the system. So the entire change of the mutual information is really the summation of this I x dot and I y dot. So when I x dot is positive, then you can say that this change from xt to xt plus dt is increasing the mutual information between x and the present state of the yt. When it's negative, then there is some kind of erasure of information. So this information flow is also a thermodynamically meaningful quantity. So you can follow up these equations. So like a mutual information flow is defined like this, as in the previous slide. And now you can use the definition of mutual information to get to this formula, and you can cancel some terms. And then what you get in the end is like the first part of this right-hand side is the total entropy change due to the dynamics of x. So it's really like a, like how the total entropy of the system containing both x and y changes because of the change of x from xt to xt plus delta t. Now you can also actually check that this total entropy change is really the summation between this x dot and sy dot, if it is defined like this. Now the other part is the change in the marginal Shannon entropy of x. So you should actually bear in mind that like these terms and these terms are not really the same. So in fact, this information flow Ix dot is actually the difference between these two terms. Now, the second law of thermodynamics holds for the total system. So like when the system consists of two parts, x and y, then we can first of all think about like the Shannon entropy of this system consisting of x and y. And there are also like reservoirs coupled to x and y separately. Then the total entropy production is the sum of this system entropy, the Shannon entropy of the system, plus the entropy change of the reservoirs due to the heat exchange between the reservoirs and the system. So this entire thing should not be less than 0. But then you can ask about what would be the apparent second law of thermodynamics for each subcomponent of the system, for x and for y. Now, so this study almost 10 years ago by Jordan Horowitz actually thought about this problem, and he showed that so this entropy production due to the change of x minus the entropy production coming from the heat exchange between the reservoir and F part should not be less than 0. So this was proved in this study. But then if we combine this together with this formula about the stochastic information flow, the information flow we derived in the previous slides, then you can see that this term is not bounded by 0, but by this Ix dot, the information flow. So as you can see, this S dot X is like how the Shannon entropy, the marginal Shannon entropy of the system changes as the system evolves. And this is like the heat exchange between the X part of the system and the reservoir. So if you just look at this quantity, this will give you the apparent entropy production for the subsystem X. So it's as if you are just forgetting about this part, and you're only considering this part, and this will look like the entropy production of the subsystem X. Yeah.
So shouldn't the entropy be additive? Like if you take two of the subsystems, then shouldn't the information come
By additive, you mean between x and y?
Yeah.
Not necessarily. I mean, there can be correlations between x and y building up, which.
I'm asking my question.
Yeah. So I mean, we are thinking about a situation where the additivity doesn't hold. In fact, yeah. Precisely, I(x,y) is quantifying how much entropy is reduced by fixing the state of x. So.
Right. So if they are independent, then it would be additive.
If they are independent, it will be additive, but it is not in this situation. Okay, so when Ix dot is negative, then it will look like as if like this is not bounded by 0, but by some negative value, so entropy production may appear to be like a negative. I mean, this inequality just says that this kind of apparent violation of second law can happen without actually violating the true second law of thermodynamics for the total system. And also, provided that this entire system is in the steady state, then you can show that this ix dot and iy dot should actually be like sum to 0. So like when ix dot is negative and iy dot is like positive, that means y is gaining some information about x through the process. So in this case, y is actually acting like some sort of Maxwell's demon for the subsystem x. So that leads to the apparent biorelation of the second law for x. So this kind of perspective can be applied to something which we study as like a freshman in the physics. So here we are looking at the heat engine coupled to hot reservoir and cold reservoir. So like as the energy and heat flows from Tx to Ty, the system in the middle manages to extract work from it. But now let's say the system consists of two parts, x and y, and we are thinking about like the steady state condition. Then in that case, the first law of thermodynamics can be interpreted as like the energy of this subsystem will not change at all because it's steady state, but like the injected heat should be like the eventually extracted as the work in this case. Now for EY, there will be like this QY dot extracted to the cold reservoir, and then there's also the work extraction. So now for subsystems, if you apply the previously derived second laws for subsystems, then what you are going to see is that like the heat flow between here and between here are kind of bounded by the information flow. By the way, so here we are not looking, we have some quantities equal to 0 because this is in the steady state. So you can apply, you can combine these relations and obtain this inequality derived by Litton and Seba last year. So this is called information flow arbitrage relation. So this shows that the work extracted from this engine is actually bounded by the information flow between x and y, as well as the difference in the temperature between the two reservoirs. So this is a very interesting relation. So both the temperature difference and information flow has to be there for work to be extractable in this system. And you can also define like quantities like subsystem efficiencies, assuming that this works as an engine. So Ix dot has to be negative in that case. Then you can say like this X part is behaving like some kind of information-driven engine, converting like the information loss to the work. And this Y part will behave like Maxwell's demon, so there is some kind of work which is converted to information gain. So,
sorry,
yeah. Yeah.
So what exactly are you meaning here by information?
Can you wait?
So what exactly do you mean by information here? Can you give me like some concrete example of what would amount to like production of information in this system?
It's like, like by changing the state of X, you are kind of reducing like how much uncertainty you have in the like Y.
I mean,
right?
I'd really
So,
appreciate an example, a concrete
an example. Maybe we can get to that later. Yeah. I mean, because actually I'm going to kind of show you some examples later on. Yeah. Okay, so you can also do this for the active engines. Like previously this was for the passive heat engine, but now you can add some kind of like a bacteria-like particles in this hot reservoir. And that doesn't have to be hot reservoir even. The temperature can be equal in this case. And so, I mean, to make the model concrete, you can also think of this as some sort of a model like this. Like if you didn't have this part, then this model will perfectly be like the just heat engine, passive heat engine, but you have some extra self-propulsion force, which is given by the Ornstein-Uhlenbeck process. So this is actually like the active Ornstein-Uhlenbeck process coupled to the engine. Then you can also interpret this thermodynamically and have this extra active work getting injected into the system. Then in that case, the work output is going to be bounded not only by the information flow, but also by this injected active work. So in this case, the information flow is not constraining W out the power of the system. So what you actually end up getting is like something like this, like this. This horizontal axis is like some kind of non-equilibrium parameter fixing the level of some kind of non-equilibrium driving force of this system. And this vertical axis shows some various thermodynamic quantities. But what is important here is that while Ix dot changes sign as you change the parameter, still this work output, the regime where this whole thing operates as an engine with positive W out dot, actually this regime exists on both sides of this red dot, this dashed line. So even when like the information is gained or lost, this thing still like works as an engine because of this activity in this reservoir.
Is it a kind of a Brownian gyrator? So
it is a sort of Brownian gyrator, yeah. I mean, not a sort of, but a Brownian gyrator, yeah. Small x in the first equation, this is the active Ornstein-Uhlenbeck noise. So, so this makes the dynamics x more or less like the AOUP coupled to some other things. Okay, so yeah, so as I've shown you through these examples, the information flow defined so far is really thermodynamically meaningful. It gives you some bounds on how the energy can flow between like components of the system. Now, but I would like to point out that this information flow has some like limitations. So it is defined only for an ensemble of trajectories. So, so it is basically some kind of averaged out effect. But there might be cases when you can define information somewhat like a fluctuating quantity, so that like maybe you can think about the situation where the whole system consists of two equal like subsystems. They look exactly like each other. Still, they are coupled to each other, so they might be exchanging some kind of information. But what happens is that like in the steady state, since these two are just the same, like the Ix dot plus Iy dot has to be 0, and both Ix dot and Y dot has to be 0 because these two subsystems are equal to each other. But then that doesn't actually mean that there's no information exchange between these two systems. Their states can still be correlated when we just measure them in the middle. So, so that's why we want to think about stochastic information flow, which is the stochastic version of the quantity defined previously. Okay, so, but actually we found out that was done in the previous study, in fact, which was by Horowitz again. So, so their approach was basically like this. So they first of all define the stochastic version of mutual information. So mutual information is really in this thing, average over the joint distribution of x and y. So when the x and y are not independent, then this is non-zero, and you are getting some positive value for this mutual information. But this is like the stochastic version. So if you average over this, then you get the mutual information we usually talk about. But this is defined for each state x and random state x and y. Now, if you define stochastic version of mutual information like this, then naturally stochastic information flow can be defined using the change of this stochastic mutual information. So again, you are thinking about like how changing the state of x is going to change this quantity. So that gives you the stochastic information flow. Now, to be precise, if you take the time derivative of this stochastic mutual information, you actually get 3 components, like the jx dot, jy dot, plus, so these two are actually coming from the change in the state of the system. But when you, this quantity actually also contains dependence on like a p, the distribution p itself, and the p can change in time if it is not in the steady, if the system is not in the steady state. So there can be like a component coming from the change of the probability distribution, but then if you just try to focus on the steady state, then this part will go away. So throughout this study, we are going to assume that we are staying in the steady state. Well, maybe we can also try to deal with this thing, but like this part actually turned out to be challenging when you want to measure, infer some stochastic information flow from actual trajectories. So we are going to focus on the case when this thing is 0. So assuming that for various kind of stochastic dynamics, you can actually represent this quantity as in terms of the transition rates or dynamics of the system. So for example, for Markov jump dynamics, you can express this in terms of these conditional probabilities and like the hopping rates. And also for like a Langevin dynamics, you have this formula, which relates to the change of x and the conditional probability to the information flow. Now, so these people actually show that this stochastic version of information flow obeys integral fluctuation theorem. So a corollary of this is that when you take the average of the exponent, then it has to be greater than or equal to 0. So you recover the subsystem second law as a corollary of this integral fluctuation theorem. So okay. So basically, people have defined stochastic information flow, but what we found lacking was like how does the dynamics of the system or the thermodynamics of the system actually looks like when you put a constraint on this stochastic information flow. So are we really going to get some violation of the second law of thermodynamics in an apparent sense when we really observe this SIF value not being equal to 0, for example? Okay, so yeah, so this is like one example that we have seen. So in this case, we again have this Brownian gyrator-like system, but the temperature is equal. So this system is actually in equilibrium in the steady state, and there should be no flux in the x and y space when you just observe the average behavior of the system. Unconditional behavior of the system. But then now we are introducing some constraints on the value of this Ix. Sorry for the notation. This should have been more like curly Ix, meaning the stochastic information flow. This is not the average version of the information flow. This is the stochastic version. So we can plot, for every trajectory of the system that we observe through the simulation of the system, you can plot the value of Ix in the horizontal axis, and on the vertical axis, you can plot a sort of a stochastic area formed by this trajectory. So here,
area is the same as angular momentum here.
So okay, it's angular momentum. So this system is overdamped. So I mean, I cannot say angular momentum, but it is sort of similar. So I mean, this is really the directed area enclosed by this curve. Okay, so there are like two stars you can see here, and we are showing you. I mean, there are data points here, and we are showing you what the trajectory drawn by the system looks like in terms of x and y in these 2 points. So here, the information flow is actually like x is like losing information about y. Then in this case, as time goes on, I guess the time actually goes from here and here. So the system is doing some sort of like a counterclockwise rotation around the origin. So this is actually what really happens when x is losing information about y. And when you have the opposite sign of Ix, like in this example, then you actually see this kind of behavior. And as you can see, there is a rather strong correlation between the value of Ix and the value of Axy, the stochastic area. So you can see that they are sort of exhibiting a negatively correlated behavior. So by conditioning on Ix, you are effectively making the system, driving the system out of equilibrium in a sense. So there is some kind of circular current exhibited by these two particles. which would happen, which you'd expect in a Brownian gyrator-driven out of equilibrium. But in this case, you are actually making that driving by conditioning on this information flow. So you can see that the correlation between these core quantities are always negative. Yes, I also, here we've seen the dynamics, and also you can check the thermodynamics aspect of this system. So again, we have the same system, but now we are, instead of this stochastic area, we are plotting the amount by which X appears to violate the second law of thermodynamics. So when the second law of thermodynamics holds, then the value of this quantity should be like above 0, not less than 0. But what happens is, like, for the subsystem second law, the actual bound is given by this dashed line on average. Now this dashed line is the correct bound when you think about when you think of this Ix as an average quantity, but this is not an average. This is like a fluctuating quantity. So this violation can actually be like the less than what is given by the lower bound given by this Ix. But still, what you see is kind of a sort of good correlation between these two quantities. So, so more or less the amount by which you violate this bound cannot really like grow to a large amount, but like the trend roughly follows this lower bound set by the inequality. Now you can do this for the overdamped particle. Actually, like in the previous studies, the bound was proven for the overdamped particles, but we extend the proof to underdamped particles as well, and you actually it turns out that the similar behavior is also observed for the underdamped particles. Okay, so so far I've just shown you some results that we get for finite trajectories, like trajectories that are observed only for a finite window of time. But then now you can extend this to trajectories of infinite length in time, and you can think about large deviation properties of this system. So you can take the time average over this infinite observation time, and you can think about like how the values of these quantities deviate away from the expected time averages. And in that case, you would expect that the system would exhibit large deviation principle. And to explore this principle, you can calculate the scared current generating function for the time averaged stochastic information flow. So this J tau is really averaged over this observation time tau. And what we know is that this large deviation function defined like this, so that it really quantifies like how rare a deviation away from some like average value of J tau is. How rare these deviations are. And okay, this should have been actually tau, in fact. Okay, so then this large deviation function can be determined by taking the Legendre functional transform of this scared current generating function that you obtain. So everything just boils down to calculating this scared current generating function. And we can do that basically. I mean, that system is a linear system. Well, what slightly complicates the matter is that like this J tau, the stochastic information flow, is not a linear quantity, it's a bilinear quantity. But still, like the question of obtaining the scared current generating function becomes equivalent to solving a sort of this equation called Riccati equation. And we developed some kind of method which can do this for like arbitrary dimensional systems. Okay, so for this active engine model that I showed you previously, we basically did that large deviation analysis. And what we see for the large deviation function is that, as you can see here, so this is the large deviation function curve, and there's some point beyond which the system has some sort of phase transition. So there's a singularity here, and after this point, the large deviation function just becomes a straight line. So what happens here is that, like below here, when the system exhibits some sort of deviations from the time average value of I tau, the stochastic information flow, then this kind of system looks as if, this conditioned ensemble of trajectories looks as if the system has formed some alternative steady state profile, which supports this deviation from the average value of information flow. And then beyond this point, the main contribution to the deviation from the equilibrium behavior, the average behavior, comes from some kind of transient effect. Like the system goes to a very rare initial state, and by relaxing from that initial state, the system actually exhibits this deviation. So there are like two very different dynamical modes of system contributing to these fluctuations that leads to this dynamical phase transition. And what we can see from the conditioned ensembles revealed by this large division analysis is that by conditioning on the stochastic information flow, you can change the extracted power of this system, of this engine. And as you decrease this active driving force, which is here, driven by this delta mu here, then what you see is that this actual power you achieve is pretty much close to the bound you set by this information flow arbitrage inequality. But then as you increase the activity, the self-propulsion force, then you start to see that this power actually goes higher because there is some extra contribution to the lower bound coming from the self-propulsion force. Okay, so also you can see that by imposing these conditions, you are seeing some sort of a stronger non-equilibrium current you observe in this state space of the system. Okay, so now, so far I've shown you that by conditioning on SIF, you can make the system look as if it is violating the second law. Although there are no strict bounds, still you see some nice correlations. So this shows you that if you just look at the stochastic information flow from the trajectory, then it can serve as a sort of indicator of how much the trajectory seems to violate the second law in the subsystem sense. So now the question boils down to whether we can actually grasp the SIF, the stochastic information flow, when we look at some kind of trajectory. So far, I've just shown you some exactly solvable models, but not all systems are solvable, and in most cases, most useful cases, we don't really know how to solve the system. So now our question is how to estimate the quantity just given some sort of empirical trajectory. And it turns out that this can be done. So how do we infer the information flow from the actual trajectory? So we can do so by, first of all, estimating the stochastic mutual information. And stochastic information flow can be guessed from the time derivative of this stochastic mutual information. And the stochastic mutual information can be inferred by various means, but one of the most maybe notable way was to use the artificial neural network. So by doing some sort of optimization of this neural network, you can construct some network so that when it is given the trajectory, then it just spits out the information flow, the mutual information between x and y. Okay, so there was this method already proposed in the literature, but we actually improved this using some alternative optimization function or loss function. So here is what we propose. We call this alpha mine, because there's some free parameter alpha here. And what we optimize through this learning process is this alpha divergence between the joint probability distribution and this product of the marginal probability distributions. And there's some free parameter alpha, which can range between -1 and 0. So this is really the loss function, and this is what you call the alpha divergence in the information geometry literature. So when in the previous method, the mine, it corresponds to a case when this alpha is equal to 0. So when you send alpha to 0, this is also 1. 1 minus 1 is 0. This is also 0. So this actually becomes, if you carefully take the limit, then what you get is the Quebec-Libler divergence. So people use Quebec-Libler divergence to estimate the mutual information between x and y. But actually, the loss function doesn't have to be equivalent liable divergence. It can be more general. And what we see is that by making this alpha equal to -1/2, which corresponds to the case of Hellinger distance, you can make this measure more robust against sampling noise you get when you don't have enough trajectories in your data set. That's because when alpha is like a -1/2, then as you can see here, this becomes -1/2. This becomes just 1/2. Now, what's problematic about this loss function is that like there are cases where, for example, j theta can be very large, but the probability of having large j theta is very small. So while this value is large, the probability of absorbing that event is very small. So this is subject to very strong sampling noise. But then you can kind of minimize this effect when you choose alpha equal to -1/2, because then you can make both terms more or less kind of balanced to each other. So that we actually found that while we were studying applying a similar method for the entropy production, and we actually kind of showed that, like, okay, unfortunately this is cut off, but as you increase the non-equilibrium driving, you are sort of making this problem more difficult to learn. But then what you find out is that like the alpha equal to -0.5 case achieves the minimum mean square error of the entropy production. So we can expect the same for this mutual information estimation problem as well. And then you can use this loss function with alpha equal to -1/2. So the neural network architecture looks like this. It's just the very trivial, sorry, not trivial, very widely used fit for neural network architecture. And you can basically train this network to get the correct value of, sorry, the estimated value of this stochastic mutual information. Okay, so now the question is how well this method estimates the actual information flow for systems. So first of all, to test the performance with some benchmark, we construct this n-bit system with every pair of bits connected by a harmonic oscillator. And what we saw is that here we are increasing the number of bits in the system, and then we are measuring how much information flow from one bit and the rest of the system. And you can see that this is the average value of the information flow. And you can say that as you change n, the agreement between the theory and prediction is kind of like this. And when you measure the diffusion coefficient for this information flow, then also again you see some kind of roughly close agreement. And what I want to emphasize is that even if I increase n, the performance does tend to get worse, of course, because you're certainly going to need certainly many trajectories to get the correct estimate, and that becomes difficult when the system becomes larger. But the performance is more or less scalable, as you can see here. Okay, so now that we have obtained this, and we know that we can apply the system to many body, the case when the system has many particles which are interacting via potentially like a nonlinear potential, via nonlinear dynamics. So now we apply this scheme to the Graham-Motor model. So Graham-Motor model is a model of synchronization where the phase of each particle is driven by some angular frequency, and the phase wants to be together. And there's also some noise which are potentially driving a system. And the overall parameter measures how synchronized these oscillators are. And basically, we know how to get the correct transition point for this kind of system. And now we are applying our method to this system, and we can measure how the information flow between between different parts of the system in the synchronized state and desynchronized state. Okay, so we actually did this for the case when the oscillators consist of two different kinds of oscillators. So there are two populations, one driven clockwise, the other driven counterclockwise. And so as you increase the driving frequency, you can see that the order parameter decreases. And you can actually estimate the exact, obtain the exact transition point using your some theory. And what happens here is like if the driving frequency is stronger, then the two populations become basically independent of each other. So you lose the synchronization. And now so this is the synchronized state for small driving frequency. This is the desynchronized state for large omega C driving frequency. And what you see in terms of the stochastic information flow is that the mean stays very close to 0. This is expected because in the steady state, X and Y are identical, and they cannot really exchange anything on average. But if you measure the variance of the stochastic information flow, more precisely the diffusion coefficient of the information flow, then you can see that the quantity stays close to 0 in the desynchronized state, but it jumps to a large value when the system is in the synchronized state. So this is certainly very intuitive and makes sense. Only in the synchronized state, the two populations can exchange information and try to follow each other. Yeah. Mean of stochastic information flow and variance of stochastic information flow. Yeah, sorry for missing the notation. Okay, so finally, now that we have seen how this measure works for a stochastic system, a model system, now we want to apply this to a realistic system. So here here I'm showing you the dynamics of two actual cells. On the left side, you are seeing, actually I forgot which one is cancerous and which one is non-cancerous, but okay. One of them is like a pair of cancerous skin cells of a human being, and the other one is non-cancerous cells. And so since the system is the system has two chambers which are coupled by, connect to each other through some very narrow channel. So when the two cells meet, then they can either actually I think I can. Okay, yeah. So as you can see here, when these two cells meet each other, they repel, and like the cell which wanted to go to the other cell's chamber is kind of repelled back, like it goes back. So there is some kind of reversal of the cell movement here. But on the But then on the right-hand side, what you can see is that these two cells actually slide by each other and exchange position. So there are reversal and sliding events for these two kinds of cells. So you can actually measure I think this is like the trajectory of the nucleus of the cells, of the two cells. So you can measure what is the position of nucleus changes in time. And you basically have these trajectories for many, many different kinds of experiments. And some of them belong to two cancerous cells, and some of them belong to two non-cancerous cells. Now, if you measure the mutual information between these two cells, then there is not that much difference between the cancerous case and the non-cancerous case. So the mutual information does not reveal that much about their difference. But if you apply our stochastic information flow to this data, then what you see is that the variance of the stochastic information flow exhibits much higher value for cancerous cells than non-cancerous. So why are cancerous cells exhibiting higher information flow compared to non-cancerous cells? And you can actually try to decompose these variances into contributions from different kinds of interactions between the cells. So when you look at the trajectory, there are time windows which corresponds to this reversal dynamics, and those corresponding to the slide dynamics, and those which don't belong to either. Then you can measure how much information exchange contributes, how much each type of dynamics contribute to this information exchange levels. So what you actually see is that if you take into account that cancer cells exhibit a lot of sliding dynamics than the reversal dynamics, you can try to divide the information exchange for each type of event. And what you see is that for like a cancer cells, the information exchange level per event is generally much higher, but then the difference is much greater for the reversal events. So so essentially the bit difference between the cancer cells and non-cancer cells can be like can be measured by looking at how the stochastic information flow occurs between for each type of dynamics. So, well, it might be. Our hope is maybe this can be a sort of a diagnostic method for a differentiating between different kinds of cells. You're just using information, but well, okay. We still didn't consult the experts in this area, so maybe if you have some kind of opinion, then anything's welcome. Okay, so the take-home messages are we can, by partitioning a system into two subsystems, you can define stochastic information flow for each trajectory. And by conditioning on this quantity, you can make the system appear like it is violating the second law of thermodynamics. And what is good about this quantity is that in the steady state, you can just look at the trajectory of the system, and then using machine learning method, you can infer the quantity for a very large number of particles. And the variance of this stochastic information flow can successfully capture information exchange even when the two subsystems are exactly like each other. Okay, so these are my messages. And okay, this is my 11-month-old daughter. Sorry, right? Yeah. Being a Maxwell student. Okay, thank you very much.
Just by curiosity, concerning the system which you considered in the middle of your talk, so you have two coupled Ornstein-Uhlenbeck processes, linearly coupled.
Yeah.
Yeah. If you reason, and so coming now to information exchange, because of this just link between these two, they become correlated and they transfer some information.
Yeah.
But if you look at the currents, yeah, if you look, okay, as if you have a particle on a two-dimensional plane, you have shown the currents, and indeed you have on average some circulation of the current along closed elliptic orbits. But there is a second story. If you look, here it is. Yeah. And so definitely this correlates them. They have to know about behavior of each other instantaneously in order to make
right. Yeah.
But there is another story. If you look a little bit deeper and you calculate the curls of the current, you will see that once the temperatures are different, the curls exist, which means that not only moving along these orbits, it also spins. Like
spinning
Earth
by
going around the sun, it also rotates around the center.
Okay, I see. Yeah.
And now coming back to the energy, to the information transfer, can you disentangle both relations?
That's a very interesting point. Actually, I wasn't aware of that. Maybe that would be a very interesting thing to check.
Very nice talk. So in the cancer cell that you were talking about, so how do you divide subsystem A and B when you're talking about stochastic information flow? Because they actually join together and they just come.
So it's just you can draw any line effect. The only condition is then you divide the system into two mutually disjoint subsystems.
But how do you do? Because they just join and disjoint. So, how do you do that?
How do I do that?
Yeah. Because I didn't understand how do you divide. Say this is subsystem A, this is subsystem B.
How do you divide the system into parts A and B?
Yeah.
Well, any choice is actually possible. In fact, provided that you just divide the coordinates into two different parts.
Spatially separated regions.
But okay, of course there will be some cases which makes more sense to do that. For example, in our case, our main motivation was to quantify the information exchange between two identical objects. So therefore, like for example, in the case of this synchronization, we made two different populations which look exactly like each other, and then we just chose each population as the subsystem.
Okay.
And also for the example of cell, the cells look very, very much like each other, so we chose each cell as like subsystem. But well, I mean, you can just name your choice.
And can I ask one more question? Can I ask one more question?
Yeah, sure.
So, like in cancer cell, normally people measure entropy production to classify if this cell is going to be having a cancer or not. But like here, you are computing information.
Yeah.
What information do you get from there? Like you are showing the variance is higher for some sort of cell, but not for other ones. But I didn't understand that. Okay, what exactly information do you get from there?
So basically, by measuring the information flow, we can quantify how much dynamics of each cell is affected by the presence of other cells. So what you see is like for cancer cells, there's much more active interactions between cells, in fact. So, so this information flow is, I mean, compared to entropy production, is directly related to that question. So I think this might be a more useful measure.
Okay, so let us break here, and we come back at 11:30.
Okay, thank you.
People for the records last day, the Brumley. I think you must have got the email from the secretary. Please reply the date that we see on the vehicle.
Very nice talk.
Yeah,
I
thank you very
really
much.
enjoyed it.
I just wish I had
Yeah,
more
but
time to do it.
it's like normally when there were like couple of questions. Like one of them is like when we were discussing when I was in David Swag's group. So now when we on an average level, when you can divide subsystem A and B,
Yeah.
but there's still ambiguity that how you divide internal energy.
Internal region.
So, for example, if I write a particle A, particle B, and interaction.
Yeah.
So the interaction, I have infinite choice that I can divide that interaction in terms of A and in terms of B.
By infinite choice, what do you mean?
For example, I can choose I can set up my choices. Like for example, I have h of x, h of y, and then h of xy.
Yeah.
And then if I call this is my subsystem A, I have to divide that interaction energy to
Yeah. Still.
the
Sorry.
interaction energy to be part of A or X. Then how should I because this is like arbitrary in the representations of did you understand your question? Like when you classify a system, I mean now since you have very good examples of undirect or spin system, but for example if I'm looking at a very complicated system as then I don't know what is A and what is B and how to divide it. This is quite arbitrary. A and B they independently themselves, and when they're interacting with the upper system, there's the information flow and energy flow. But to the partition, and that's quite arbitrary.
This should be pasted upside.
If you are suspecting that it won't, it will change the power. It will change it. Microscopic
Come on.
you are on time, everybody else is not.
It's okay.